This video is on quantum computing. Quantum computing creates qubits from particles such as atoms or particle of lights, or objects that mimic them such as superconducting circuits instead of bits. What does this mean? Well, classical computers today employ a stream of electrical impulses in binary. It means it uses 1 and 0 to encode information in bits. Quantum computing will employ 0, 1, and a superposition of these to encode information in qubits. What is superposition? Superposition is when it is in a complex combination of both 1 and 0. Superposition is basically a system that has two different states at the same time that can be measured in multiple ways. For example, an electron has two possible quantum states, spin up, spin down. But since superposition principle says that if a quantum system can be in both states, then it can be placed in a linear superposition of these states. So electron can be both up and down at once, and it becomes a complex combination of both. Simply put, bits can hold 0 or 1, and qubits can hold 0, 1, or any proportion of both 0 and 1 at the same time. However, the continuous nature of the state is not the most important distinction. It's a fact that multiple qubits can exhibit quantum entanglement. Entanglement is a non-local property that allows a set of qubits to express superpositions of different binary strings simultaneously. While quantum computing sounds nice, there are some limitations that needs to be discussed. First, we have decoherence. While it's easy to store information at 0 or 1, storing a quantum state is difficult and has to be shielded electromagnetically, and temperature has to be cooled down to absolute 0. Qubits simply require precise physical conditions to function. However, the beauty of qubits is that if hacker tries to observe them in transit, their fragile quantum state is going to collapse to either 0 or 1, which means that hacker can't tamper with qubits without leaving behind a sign of activity, which is good for communication. Quantum communication technology may have uses for secure communications, quantum networking, and future quantum internet. And lastly, let's talk about how quantum computers pose a threat. The Quantum Computing Cybersecurity Preparedness Act requires U.S. federal agencies to upgrade post-quantum encryption and to report their progress to Congress. And this is because quantum computers will be able to break widely used public key cryptographic schemes, putting today's crypto systems, digital signatures, electronic identities, and such in jeopardy. Some systems might have issues due to restricted accessibilities like satellites. The transition to new quantum-resistant cryptographic algorithm is going to take years, and it's going to be complex, and there's going to be a lot of financial costs involved. However, quantum computing is not set to come out anytime soon. Projection is not until 2030. However, post-quantum cryptographic standard should come out several years before that.